So we'll today discuss about the packet scheduling algorithms for providing quality of service guarantees in internet. Till today, we have been considering that various flows, when they share the buffer at a particular router or a statistical multiplexer, then there is one common buffer where all the flows are sharing this common buffer, and there may be a packet scheduler which schedules these packets in the first in first out manners. Okay, so let me just see what is the scenario that we have been considering till now. The scenario that we have been considering is that there is one single buffer and all the internet flows are sharing this buffer, and this buffer may be scheduling the packets maybe in a first in first out manner. Now, for the time being, let us consider that we are not concerned about providing specific quality of service guarantees to the flows, but let us say that at least we want that these various flows, when they share one common output link, then they get what we call as a fair share of the bandwidth. Okay, we will shortly define what is meant by a fair share of the bandwidth and so on. Okay, but let us consider that these flows which are sharing this single common buffer are the TCP flows. Okay, so basically what we are saying is that all of these are, let us say, are TCP flows. Okay, now these TCP flows are sharing one common buffer, and the scheduler is scheduling the packets in the first in first out manner. Okay, so we would like to know that what are the problems with these scheduling disciplines. Okay, so towards that we should know that the TCP has a specific congestion control techniques. Okay, the TCP's congestion control technique is based on what is called as additive increase and multiplicative decrease. Additive increase and multiplicative decrease. What does it mean? It means that the TCP increases its window size in an additive fashion after the receipt of an acknowledgement. Okay, so when the TCP sends packets worth its window size, okay, and when the TCP keeps on receiving the acknowledgement, it slides the window and it increases the window size in an additive fashion. When the TCP's congestion control mechanism detects the packet loss, then the window drops, okay, to half of its previous size, or it drops to 1, depending upon various versions of the TCPs that are being used and the various types of congestion control algorithms that are being deployed. But the basic principle is that the increase is in an additive fashion and the decrease is in a multiplicative fashion. Typically, if you see the window evolution, okay, then this window evolution of the TCP will follow a sawtooth pattern, that it increases in an additive fashion, and whenever it detects a packet loss, the window size drops to 1, or maybe the window size may be dropping to half, depending upon the versions that are used. Okay, now note that for the acknowledgement it takes about one round trip time. Okay, the packets need to go from the sender to the receiver, and then the acknowledgements need to travel from the receiver to the sender. Therefore, this increase of the window size or this decrease of the window size, okay, it can happen at an interval of the round trip times. Okay, now therefore what happens that when these multiple TCP flows like this are sharing a single common buffer, it might be quite possible that these sources of these TCP flows, okay, have varying round trip times, okay, between their destinations. Okay, so these TCP flows are having varying round trip times, and let us assume that this of our node is a congested, or what we call as a bottleneck node or a congested node. Okay, so as a result, when these TCP flows are having varying round trip times, okay, then this congestion control mechanisms, okay, will be biased towards, you know, those connections which are having shorter round trip times. Okay, the TCP's congestion control mechanism of additive increase and multiplicative decrease is biased towards those flows which have shorter round trip times. Why? Because if the flow has a shorter round trip times, it ramps up to its available capacity, okay, very fast, and when it detects the packet loss, when the bottleneck node is congested, it drops its window size to 1, but then it ramps up again very fast. On the other hand, the flows which are having larger round trip times, they respond to the congestion conditions and then ramp up their window size, you know, proportionate to its round trip time. So if it is large, so the increase is little slow. So therefore, the AIMT method is biased towards connections with the shorter round trip times. As a result, what happens when these TCP flows are sharing a single buffer at a node which is scheduling the packets as a first in first out manner, then obviously the flows with shorter round trip times are likely to have an unfair share of the bottleneck bandwidth. Okay, so this is one aspect of when the various flows are sharing a common buffer, then we would like to know whether each of these flows are getting a fair share of the output link bandwidth. Even if these are not TCP flows, some of these flows could be the non-TCP flows also, and suddenly they may start transmitting a large number of packets. Okay, now if they transmit the large number of packets and congest the link, then the packets will get dropped, and the TCP in response to this packet drop will drop its window size. But on the other hand, the non-responsive flows may not drop the packets and keep transmitting the packets, as a result hogging the bandwidth and getting an unfair share of the link bandwidth. So the question therefore is that we need to segregate, you know, these flows into various queues and then schedule the packets in such a manner that each of these flows gets a fair share of the link bandwidth. Essentially, it means that we need to go to some kind of a non first in first out or non first come first serve kind of a scheduling techniques. Okay, so for both, you know, for protecting the flows from misbehaving users or non-responsive users, as well as for the users giving a fair share of the link bandwidth, we need some kind of a fair scheduling disciplines. And then we will also see, you know, how we can provide the specific quality of service guarantees like the delay or the delay jitters to these various flows. Okay, so today, you know, we will see that how we can design scheduling disciplines, you know, that meets our objective of providing fairness to various flows which are sharing our router link, as well as, you know, protecting these links from the misbehaving or non-responsive flows or even non-responsive protocols like the UDP or the constant bitrate flows or the CBR traffic, let us say in an ATM switch. Okay, so we will discuss today about, you know, those scheduling disciplines. Right now, you know, let me just discuss about these various scheduling disciplines. Okay, what are the functions of the scheduling algorithms? Okay, so functions of scheduling. What we mean by the scheduling algorithms? Okay, now it has two orthogonal components. Okay, one, you know, it decides the order of service. Okay, and second, it manages the queue of packets. Okay, so there are two orthogonal components of a scheduling algorithm. You decide the order of servicing the packet, that is which order you want to service the packet, and secondly, you will manage the queues of various packets. Now, various objectives, you know, a scheduling algorithm need to satisfy. One, as we have just spoken, is we would like to schedule the packets in such a manner that each of these flows gets a fair share of the link bandwidth, as well as they are protected from the misbehaving users. Secondly, we would also like to have some kind of a network level quality of service guarantees in terms of the delay bounds, in terms of the bandwidth, in terms of the delay jitter. So these kind of quality of service guarantees we would like to give through the scheduling algorithms. And secondly, we would like to have some kind of hierarchical link sharing. By hierarchical link sharing, we mean that there may be a link which may be shared by let us say multiple departments of an organization, and so in that department, so basically that output link bandwidth which you may have to a service provider, that is being shared between multiple departments in a fair manner, and then within each department there may be multiple applications where this link bandwidth may be shared. So as a result, we are sharing the link bandwidth in a hierarchical fashions through the scheduling disciplines. Okay, so these are the three objectives that a scheduling discipline has to meet. Then the scheduling algorithms can also be a work conserving scheduling algorithms, or it can be a non-work conserving scheduling algorithms. Okay, so the scheduling algorithms can be work conserving, and non-work conserving. What is a work conserving scheduling algorithm? In a work conserving scheduling algorithm, a server is never idle if there are packets in the queue. It always serves packets if there are non-empty queues. On the other hand, in a non-work conserving scheduling algorithm, even if there are packets in the queue, a server may be idle. Okay. The question of course is that why one would like to have a non-work conserving scheduling algorithm? Because a non-work conserving scheduling algorithm, it seems, will wait even if there are packets in the queue, and therefore wasting the link bandwidth. So why we would like to have such a scheduling algorithms? We will see later on in the discussions on the non-work conserving scheduling algorithms that sometimes it may be desirable to use non-work conserving scheduling algorithms to regulate, let us say, the burstiness of the output streams. Okay, we may like to regulate the burstiness of the output stream, because otherwise if you schedule these packets, then the downstream nodes may receive bursty inputs. Okay, so we may like to regulate this. So to achieve this objective, we might want to have a non-work conserving scheduling algorithms. Non-work conserving scheduling algorithms can also be used to control the delay jitter. Okay, to achieve these kind of objectives, sometimes it may be necessary for the server to remain idle even if there are packets in the queues, and that's why we call such scheduling algorithm as non-work conserving. For the time being, for most of these discussions in this lecture and the subsequent lectures, okay, we will concentrate mostly on the work conserving scheduling disciplines. However, I will take a few examples of non-work conserving disciplines also, and will try to illustrate where they can be used in the actual routers. Okay, so now let us see the work conserving scheduling algorithms only for the time being. Right now, in the work conserving scheduling algorithm, interestingly, there is this scheduling conservation loss. Okay, so that is what I would like to illustrate. Okay, which we call it the scheduling Klein-Rock's. It's a Klein-Rock's scheduling conservation law. Now, first thing we should know that the first come first serve scheduling algorithms, okay, where we were considering earlier that there is one single buffer and multiple flows are sharing this buffer and the packets are being served in the first in first out manner. Such first come first serve scheduling algorithms cannot differentiate between different connections. Okay. So if you have to give fairness, if you have to give protections, if you have to give quality of service guarantees, then we must resort to non first come first serve scheduling algorithms. Okay. So by the non first come first serve scheduling algorithms, we mean that we have different queues for different flows. So let's say 1 to n flows are sharing these different flows, and then there is a scheduler which is trying to schedule, you know, the various packets out of these queues, okay, and may try to give you know, certain quality of service guarantees. However, if this scheduling algorithm, if this scheduler is a work conserving scheduler, then we have a very important Klein-Rock's conservation law. Okay, so what's that Klein-Rock's conservation law? Now this states, let's say rho I is equal to lambda I xi. Okay. Now let's say lambda I is the arrival rate for the ith connections. Okay. So lambda I is the arrival rate for the ith connections, and let us say that xi is the mean service time lambda I is the mean arrival rate and xi is the mean service time of ith connections. Okay, and lambda I is the mean arrival rate or the average arrival rate of I. So lambda I xi, okay, gives you, okay, the rho I, and the rho I we call it to be the mean utilization of the link. Due to I. Okay. Now let's say that Qi, okay, is the queuing time, average queuing delay of ith connections. Okay. Then the Klein-Rock's conservation law states that the sum of rho I Qi is going to be a constant. All right. So what does it say? That suppose we have a non first come first serve schedulers where there are multiple connections. Each of the connections, let us say, is having a queue, and these queues are being served by a work conserving scheduler. Now these queues could be virtual or physical. In a practical systems we are not right now bothered, but let us say that there are n such queues. Let's say that in an ith queue, lambda I is the average arrival rate and xi is the average service time. Then lambda I into xi denotes the mean utilization of the link to the ith connection. Okay. Now what the Klein-Rock's conservation law is stating is a sum of the mean utilization due to the ith connections multiplied by its queuing time. Okay. And the sum over all such connections is going to remain constant. What is the significance of this? The significance of this is that if you want to reduce the queuing time or queuing delay of some connection, okay, let us say that of the ith connection you want to reduce its queuing delay, that is Qi you want to reduce. Okay, so here, you know, this Qi you want to reduce. Now if you want to reduce this Qi, it can only happen, okay, at the expense of an increase, okay, of the delay of the other connections, okay, because the sum of the mean utilization multiplied by the queuing time is going to remain constant over when sum taken over all connections, okay. We can give lower delays or lower bandwidths to other connections only at the expense of an increase in the delay, okay, of the other connections, okay. So we can give lower delays to the other connections at the expense of an increase in delay of the other connections. Essentially what it is mean is that utilization times the delay, okay, gets conserved, okay. So you can only play, you know, between the delays of the different packets, okay. This sum however is going to remain constant over the all connections, okay. Now this is important because what does it mean is that you cannot arbitrarily schedule connections having arbitrary delay or bandwidth requirements, okay. We need to then see that whether, you know, a particular set of delay vectors and the average arrival rate or the utilization vectors, whether they are schedulable under the work conserving scheduling disciplines or not, because, you know, we have the Klein-Rock's conservation law in place. So this is very important. What does it try to say is that we cannot design a work conserving scheduling algorithm to give arbitrary delays and arbitrary bandwidth guarantees, you know, to various flows. We can only do that with a non-work conserving scheduling algorithms, because in a non-work conserving scheduling algorithms a server will remain idle, okay, even if there are packets in the queues, and as a result, you know, in order to give a you know, it can therefore essentially you know, decouple the delay and the bandwidth guarantees. In this case, the delay and the bandwidth guarantees, you know, in some sense are coupled. However, note that you know, typically in a non-work conserving scheduling discipline, the average queuing delay suffered by connection will always be higher than the queuing delays than the average queuing delays in a work conserving scheduling disciplines, okay. So what therefore we see now in the work conserving scheduling algorithms is the bandwidth and the delay guarantees are coupled, and at the same time the conservation law holds good, okay. So this is one important factor in the design of a non-FCFS scheduling algorithms, right. Now let's move forward and let's try to see what are the various attributes of a scheduling disciplines, okay, that we would want to have. What are these you know, various attributes? So basically, you know, our objective is to design a work conserving scheduling algorithms which operates under the principles of the this conservation law, but we would like to know now what are the other attributes of the scheduling algorithms. Okay, one is we would like to have implementation simplicity. I'll just elaborate on that. Second, we would like to have fairness. I mean, this is the objective with which we really started this topic, of fairness and the flow isolation. And thirdly, we would like to have the algorithms which are scalability. We need to provide the QoS, and we need to have a simple admission control algorithm. Now let's look at the point of the implementation simplicity. Okay, if you look at the implementation simplicity, then the scheduling algorithms must be very simple to implement. Okay, now in order to give the quality of service guarantees to the various flows, we cannot afford to have the scheduling algorithms very complicated. Now, to give you an idea, if you really want to do take this scheduling decisions in a fast manner, then it really depends upon how much time is available for the scheduler to take a decision depending upon the packet input rates. Okay, so that thing must be kept in mind in devising a scheduling algorithms. Okay, so note that what we are essentially having is that in a non first come first serve scheduler there are going to be various flows. Okay, and here is going to be a scheduler. Now this scheduler needs to take a decision which one of these packets it will pick up, okay, for transmission on the output link to satisfy the objectives of the fairness and the quality of service guarantees. Okay, so the scheduler has to take a decision which one of these packets it needs to pick up. Now this decision the scheduling discipline must take within certain time budget. Okay, now what is that time budget available? Now that time budget available will depend upon what is the input arrival rate to these various queues. Okay, so that the scheduling algorithm takes a decision fast in a line rate manner. Okay, so that is one aspect of the implementation simplicity. The scheduling algorithm must not do lots of computations in order to determine which one of these packets it should pick up for the transmissions. Of course, one would argue that with the present day VLSI implementations, these days you can implement very complex logic of computing which one of these packets to pick up for transmissions. Okay, so however, when we say that the implementation simplicity, of course it depends upon the time budget, but it also depends upon the amount of scheduling state which this algorithm needs to store in order to take a decision. Why? Because these scheduling states will need to be stored in a memory, and if these scheduling states are large, okay, then of course it needs to be stored in some memory which needs to be outside the chip, and if it is outside the chip the access time will be large, and therefore the time required to compute the decision will also be large. As a result, typically we would like to store the scheduling state on an on-chip memory to reduce the access time, and therefore the scheduling states, the number of scheduling states in a particular scheduling algorithms should also be small. So that is one aspect of an implementation simplicity. In order that the algorithm can scale, also the number of operations that are required should be independent of the number of connections that are there. That means it should be independent of this n. Okay, for the implementation simplicity, your scheduling algorithm should be independent of m. Typically, we would like to have the scheduling operations. Okay, the operations required in the scheduling algorithms of order 1. We don't want them to be order n. If they are order n, then the algorithm will not scale, because typically in a core routers the number of connections can be as large as 100,000 or 200,000 flows, and if there are 100,000, 200,000 that kind of flows, then obviously the number of scheduling operations will not scale if the number of scheduling operations are scaling order n. Okay, so therefore we would like to have the scheduling operations independent of the number of connections that are there. The number of scheduling states which an algorithm has to store should be smaller, and the overall number of computations or operations that are required to do should also be small, so that it fits within the time budget. So by implementation simplicity, we mean that a scheduling algorithm should not only have less number of operations to compute, but also should require less memory. So that will make an implementation of a scheduling algorithm simpler. That is one thing. Second thing is the fairness and the flow isolations. Of course, the scheduling algorithms should be fair. Okay, and as we have already seen earlier itself, that the TCP flows, the TCP's congestion control algorithms is biased towards connections with shorter round trip times, and therefore we need a mechanism at the router which can give each TCP flow a fair share of the output link bandwidth, and at the same time it can protect these TCP flows from non-responsive flows like UDPs or some misbehaving sources. So the scheduling algorithms must provide fairness and must provide some kind of flow isolations. Now of course this question is there, that what do you mean by fairness? Okay, this obviously a question. Now we will talk fairness in our discussion in the context of max-min fairness. Okay, so let me just explain what is meant by max-min fairness. Max-min fairness. So it actually means that we are maximizing the minimum fair share of the bandwidth. Right? How does it work? It works that it adopts three principles. Resources are allocated in the increasing order of their demands. Okay, so we will allot the resources in the increasing order of their demands. No user gets a share larger than its demands. And users whose demands are unsatisfied gets equal shares. Of course, you can give weights. So we are assuming that the users whose demands are not satisfied, they do not have so they are not indistinguishable in any other sense. However, if you allocate weights, then the users with unsatisfied demands will get shares in proportion to their weights. Okay, so we are assuming here that the weights of all the users are 1. Then the resources are allocated in the increasing order of their demand. No user will get a share larger than its demands, and users whose demands are not satisfied, they will get equal shares. Just to give you an example, let me just explain this with an example. Suppose there are users like with demands like x1, x2, so on till xn, right? And obviously x1 plus x2 plus xn, the sums of these demand now these are, let us say, the bandwidths, okay, which a user wants, and let us say that we have a total bandwidth of let's say n. Okay, the total bandwidth is n. Then obviously that there are n users, and one would say that a fair share would be that you give each of these n users 1 by n bandwidth, right? So we can give them sort of 1 by n. Obviously, one thing is there, that the sum of these bandwidths, may be greater than n because their demands, it is possible that these xn's, okay, may be greater than 1 upon n. So we have arranged them in such a manner that this x1 is less than x2 is less than x3 is, so xn is the highest demand. Okay, now we allocate each users, let us say 1 by n. Now it turns out that x1 happens to be less than 1 upon n. If x1 is happens to be less than 1 upon n, then we allocate to the first user the resource x1 only. Now if we allocate the resource x1, then we have a bandwidth available which will be 1 by n minus x1. This will be the extra bandwidth that gets available. Divide by n minus 1, okay. This share we added to each of these users. So now this share gets added, okay, to each of these users. Now again we take x2 and try to see whether x2 is greater than this or not. Okay. If it turns out that x2 is less than this, then obviously x3, xn all will be less than this, and then all the users will get this. However, if x2 is greater than this, then the user 2 will get only x2. Okay, and we subtract, okay, from this x2, okay, and then divide that equally among all the users. Okay, so finally, we will then achieve a fair share of the link bandwidth to all the users in the sense of max-min fairness. Okay, let me just give you an example. Let us say that there are 3 users, okay, and the user 1 has a demand of let us say 5, user 2 has a demand of let us say 8, and user 3 has a demand of let us say 10. Alright, and let us say that we have a total resources of let us say that we have 20 let's say 18, total resources of 18. Now if we divide 18 in 3 users, okay, in among the 3 users, okay, here of course I should assume that the total number of users are n and the link bandwidth was actually some kind of unity. Now if you divide this bandwidth among 3 users, then each user should get 6, 6 and 6 units. Alright, but this user has a requirement which is less than 6, so this user will get only 5, and I have 1 left which I can divide them into equal parts, okay, and make them 6.5 and 6.5. Now 6.5 turns out to be less than 8 and 6.5 turns out to be less than 10. Now I can't do anything more than this, so these users will be stuck with 6.5. So we satisfy this principles that no user gets a share larger than its demand, okay, and users with unsatisfied demands get equal shares. So if you see that these users, users with 8 and 10, their demands are unsatisfied, but they get equal shares of 6.5, 6.5, so which is actually of their fair share of the link bandwidth. Okay, so this is what is called as that we are allocating the resources in such a manner that we are maximizing the minimum share of the link bandwidth. So we are allocating the resources in the sense of max-min fairness. Okay, so one more thing which I would like to point out in terms of fairness is typically the scheduling algorithm, okay, takes only the locally fair decisions, right, because you are there at a network node where there are these non first come first serve schedulers, and there are these various queues. So when a scheduler is scheduling these packets in such a manner to give a fair share of the link bandwidth to these users, it is taking a local decision. Now remember that these nodes are connected together in a network nodes, and fairness is actually a global objectives. Okay, the fairness really is a global objectives. Okay, now it can be shown that if each source uses, okay, sticks to its smallest locally fair resource, okay, available resource, smallest locally fair resource, then it will result in a globally fair allocation. So what we can show is that if each connection or each flow limits its resource usage to the smallest locally fair resource allocation, along its path, it results and we are not going to prove this, but I am just trying to point out that in a network of nodes where the nodes are individually locally giving the fairness or ensuring the fairness, and if a flow is going through several nodes, if this flow restricts its resource allocation, its resource usage to the smallest locally fair available resource, then overall in a network of nodes it will result in a globally fair allocations. Okay. Now however, the user usage pattern changes, okay, let us say at some nodes, suddenly a source decreases its resource allocation, then it will increase the resource allocation, resource usages of the other users. Now it will take certain time to propagate this allocations, okay, to all the users. So in order that we maintain these globally fair objectives, okay, if the resource usages patterns are changing rapidly, then it may be difficult to achieve a globally fair allocations. However, the usage patterns are not changing rapidly, then each flow can ensure that it limits its resource usage to the smallest locally fair available resource allocation, and then it can result in a globally fair allocations. Okay, so that is what about the fairness aspects which we want. Typically, if a scheduler is giving a fair allocation of the resources to each of its flows, then it is also ensuring protection from the misbehaving source. However, sometimes the converse may not be true. If you are providing protection by using some kind of a traffic regulators or shapers, okay, at the ingress to the scheduler, it does not mean that you will also give a fair allocation of the output link bandwidth to the flows. So therefore, while a scheduler is trying to be fair, it will automatically also ensure that it is protecting the flow from the other misbehaving users, because that flow will definitely get a fair share of the link bandwidth. But if a node is protecting, trying to ensure the protection by using some kind of rate limiting or some kind of traffic shaping at the ingress point, then it does not mean that it will result in a maximum kind of fair allocation to all the flows. Okay, so that is what about the sort of fairness. The third point that we were trying to see is was of the scalability, and that we have already seen that in order that a scheduling algorithms should be scalable, the scheduling computations which are required for the scheduling algorithms must be independent of the number of connections that are sharing the buffer, and that will make the scheduling algorithm to be scalable. We want to have the quality of service guarantees. Now, what are the quality of service guarantees? We want to give the delay bounds. We also want to give the delay jitter. Okay, we will see that it may be difficult to give the guarantees on the delay jitter in a work conserving scheduling disciplines. For this, we may need to go for the non-work conserving scheduling discipline. As far as the delay bounds are concerned, the worst case delay bounds we can give provided the flows are rho sigma regulated. Okay. If the flows are not rho sigma regulated, then it may not be possible to give delay guarantees through a non first come first serve work conserving scheduling algorithms. By delay guarantees I mean worst case delay bound. It may not be possible to give the worst case delay bound if the traffic is not regulated to rho sigma regulations. We would also like to have one of the other attributes of the scheduling algorithms is that the scheduling algorithms must lead to a very simple admission control decisions. What does it mean? Typically, as we have seen, that a traffic source will give or specify its traffic descriptors, which in internet are likely to be rho and sigma values, and the quality of service attributes like the worst case delay bounds and so on, and then the network will try to see whether it can admit these flows or not. Now, when the network tries to see that whether it can admit the flows or not, obviously the network is trying to see whether these flows, by admitting these flows, it will not affect the quality of service guarantee. In other words, the network is trying to see that all the flows are schedulable. They become schedulable under the scheduling discipline which the particular network node is implementing. Okay, so whether these nodes are schedulable or not. So then we need to define what is the schedulable region. Okay, so let me just give you a definition of the schedulable region. Okay, the schedulable region, the set of all possible combinations of performance bounds that a scheduler can simultaneously meet is called schedulable region. Now, given a schedulable region, we can have a very simple admission control policy. Essentially, we need to see whether these performance bound, these set of performance bounds of the connections that we want to admit falls within the schedulable region or not, right? Because the schedulable region by definition is a set of all possible combinations of performance bounds that a scheduler can simultaneously meet. So all we need to do is to characterize the schedulable region of a particular scheduling algorithm that we are deploying in the work conserving scheduling discipline. Okay. Now, it is sometimes very difficult to compute the schedulable regions of a scheduling algorithms, but if we can compute that, then the network will have a very simple admission control policy. We will try to see the schedulable regions of the certain scheduling algorithms that we will discuss in our subsequent discussions. Now, these are the various attributes of the scheduling algorithms that we have seen. One of them, it should be simple to implement, it should achieve fairness, it should give flow isolations, it should give quality of service guarantees, it should be scalable, and it should also lead to some kind of a simple admission control mechanisms. Okay, it should give fairness. We are saying that it should give fairness in the sense of max-min fairness. That means it must maximize the minimum share of the bandwidth, which means that resources were allocated in the increasing order of demand. So no user will get a resource larger than in demand, and users whose demands are not fulfilled or not satisfied, they all will get equal shares. So this way, we can ensure that the resources have been distributed to different users in a so-called fair manner. Okay, there could be different definitions of fairness, but most scheduling algorithms that we are going to discuss are going to ensure this kind of max-min fairness. Now, we would just like to see what are the degrees of freedom for implementing scheduling algorithms. There are various degrees of freedom for implementing scheduling algorithms. One degree of freedom is that the priority. Okay. Now, what is the priority? The scheduling algorithms can divide these queues into low priority queues and high priority queues and so on. There could be various priority levels also, priority level 1, priority level 2, priority level 3 and so on. Now, in a work conserving scheduling algorithms, if a priority level 1 is higher than all the other priority levels, then the scheduling algorithms will serve the packets from the priority level 1 only if there is a packet in that queue. If there is no packet in the queue, then it will lead to the other priority levels. Obviously, this might lead to starvation of the low priority users if the high priority users is all the time pumping the packets into it. So therefore, if we are implementing a priority kind of schedulers, then we must have some kind of admission control and traffic shaping which will ensure that the high priority users are not leading to starvations of the low priority users. It requires an admission control mechanisms. The other degrees of freedom that scheduling algorithms can have is whether it is a sorted priority based or whether it is some kind of a frame based. Okay, so that is also, now in a sorted priority based, typically each packet will be tagged with some kind of a service tag. So whenever a packet comes into the system, it is tagged with some kind of a service tags. Now, how do you compute the service tag is a different matter, but suppose these packets are tagged with service tags and then they are sorted in the order of those service tags, and a scheduler will serve the packets in according to those service tags. So these are sorted priority based. This could be frame based. By frame based we mean that we define some kind of frame length. Okay, fixed, this could be fixed frame or this could be variable length frame. Now, the scheduler ensures that a maximum amount of traffic which can be sent by a flow within this frame is bounded. Okay, that is what the scheduler is trying to ensure. So there is another degree of freedom in terms of implementing a scheduling algorithms. Then another third degree of freedoms that a scheduling algorithms can have in terms of degree of aggregations. Okay, whether the various flows have been aggregated into one super flows. Okay, and then the scheduler is scheduling the quality of service objectives or fairness objectives among these aggregated flows. Okay, so there are various pros and cons of the aggregations that we would like to achieve at a network nodes. Okay, we can discuss that later, but these are the various degrees of freedoms which are available in implementing a scheduling algorithms. The next step that we would like to take is that, given that these are the attributes of the scheduling algorithms and these are the various degrees of freedom that we have discussed today that a scheduling algorithm has, and we would like to have some kind of a work conserving non-first come first serve scheduling algorithms. What are the different scheduling algorithms that are available today, that are implemented in practice today, that achieves these desirable objectives? So that we will take up in the subsequent lectures.